Hello, everyone. My name is Anna Fribourg. I study stars, and I would like to take you on a little journey into the cosmos. But first, I have to reintroduce someone. Meet Professor Lise Meitner. I have a couple other photos of her. Obviously, not many remain. This was her in the lab with Otto Hahn as a young woman. And here we see how short she actually was, again, next to Otto Hahn, here and Fritz Strassmann. He actually happened to live in the neighborhood of my grandparents in Göttingen, Germany. So my mom, as a younger child, used to see him walk around. So a nice personal connection. I was also born in Berlin. And as you will see in a moment, there are many connections between her and my work. There's much to say about Lise Meitner, and I don't have the time today to do so. But I would like to highlight that, of course, she did not get the Nobel Prize despite being nominated some 42 times over 3 decades. But she did win a number of honors later, including, I'm not sure if it's exactly a win, but one of the elements was named after her. And this is the only element named specifically after a non-mythological woman. It's a special kind of achievement, certainly warranted, but also just a little bit odd. So MT here for meitnerium, one of the heavy elements that are indeed not long-lived, but can only be made in the lab. So her story is fascinating and worth sharing, even though she hasn't really made it into the history books, because again, she didn't get that kind of prize that warranted that. And so I'm happy to share her story and tell you a little bit about that and what her work has done. We all stand on the shoulders of giants, and I stand on her shoulders. And I'm sure many of you do too. Before I continue, though, I would like to give credit to my friend and the producer and director of this little play, Jen Maronik from STEM on Stage. I have a little bit more about it at the end, because there is also a play about Marie Curie. And this was much inspired by that. So some 80 or 85 years later, since this discovery, what has changed? Now we know that there are no heavy elements, but physicists and astronomers are still continuing to try to understand the origin of the elements. It remains not fully understood where and how all the elements form. And that's something where I'd like to tell you a little bit more about, because this is one of the research areas of mine. And the modern challenge indeed is to understand, we don't, as the astronomers, we don't have the experiments in a lab. Our experiments is out there. We also only have one experiment, and we have to kind of make sense of it all. But it's good fun. And we still ask the very similar questions, right? What are the elements like? Where do they come from? How are they made? And I would have really liked to discuss that with her. In the absence of that, I will discuss it with you. So my talk today, a very brief version, is on the cosmic origins of the chemical elements. So you probably have heard of this before. All elements are made in stars. I would like to extend that a little bit and say, and merging neutron stars. And here you see some examples of them. There's a depiction here of 2 merging neutron stars. But let's dig a little bit into that, all right? So I will actually not say too much about old stars, but I need to give you a little bit of introduction so that you know from which angle I'm coming. Let's look at the universe. What happened early on? We had the Big Bang 13.8 billion years ago. The universe was just hydrogen and helium at the time. We don't need to worry about the little lithium. And from this primordial matter, the very first stars emerged, and they were really massive, something like 100 times the mass of the sun. And that meant they exploded really quickly as massive supernovae. why was that really significant point in the history of the universe? Because during those explosions, all the elements that were cooked up for energy generation purposes in their cores were expelled into the surroundings. So the chemical composition of the universe changed forever with the onset of the first stars. The primordial universe was no more. Then the next generation of stars now formed from this slightly enriched material. And ever since, every generation had massive stars. They added more elements, more of all the elements to the gas. And with time, we have an increasing situation of, the elements all get, you get much more and more of them. So if you want to find the oldest stars, then you have to look, and I'll explain it more in a moment, for the stars that have the least of the heavy elements in it. And we try to find these very early generations of stars here because this is about as far back as we can look with stars, or probe, I should say. And they have survived until the present day today, so I can observe them with my telescope. They are there and shining, happily kicking around. I'll show you a little bit more how we do that. So let's talk about element production. Again, I'm assuming here that you probably have heard of fusion processes. You put together protons, you get 2 helium. If you have 3 helium nuclei and you put them together, you get a carbon, you add another helium, you get to oxygen, and so forth. And why is this important? Because this is the mechanism by which stars shine. Right? They need to have sustained large amounts of energy for billions and billions of years, and that only works with nuclear fusion. And what was mentioned in the play, the mc squared here, is that the mass of the constituents, protons and neutrons, if we add up, we have 2 protons and 2 neutrons in a helium nuclei, we get to 4.03. But if you measure, so that's theory, if you measure it experimentally, the mass of a helium that consists of 2 protons and 2 neutrons, you measure only 4.00, right? So there's a little bit of mass lost, and that has been converted to energy via this equation. It's not a lot, but stars have a lot of protons and atoms in their cores, right? So it all adds up, and that's ultimately enough for stars to shine. And so this is what happens primarily in supernova explosions. You go all the way up to iron in this fusion fashion, and then the supernova explodes, and that looks kind of like this. In the inner part, you have a higher concentration of the elements that being pushed out into the gas, and then further out you have sort of dilution. That's why the concentration is lower. So imagine that to be a first star, a first supernova that exploded in the universe. And then you form your next star, let's say here or there, or maybe out here. And so they will have different abundance signatures depending on what this gas was enriched with. And then these little stars that form from there, they preserve in their outer atmosphere exactly this birth gas cloud signature. And so when we observe it 13 billion years later, it's as we would be studying this situation soon after the Big Bang, right? So that's the cool thing about old stars. They preserve the chemical composition of their birth gas clouds for us. Here is a diagram that illustrates that. Again, imagine this to be the primordial cloud. You have some stars forming, some massive ones. They explode, they dump their elemental yields into the reservoir, and then the next generation forms with this slight enrichment. And then you have this cycle go round and round and round. And with every generation, the element content is going to go up, 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 up ever so little, right? Until today. And so if you want to find the oldest stars, as already indicated, you need to find the stars that formed after this cycle had only gone around once. So one enrichment from the first stars, and then what comes from that. And so naturally, the consequence is indeed old stars contain much less of all the elements than younger stars like the sun. And so here is another illustration of that. This is what the chemical composition of at the time of the Big Bang looked like. 75% hydrogen, 25% helium. The sun, at the time of the sun's birth, 4.6 billion years ago, it had already changed. So some hydrogen has been converted into helium. This goes down, this goes up. And some helium has been converted in all the other chemical elements together, combined, so 1.4%. Today, we're at about 2 point something percent. It's going to go up faster and faster, but we're not going to live in an iron universe anytime soon, so you can keep reading. And I just have to throw that in for general education purposes. This is the astronomer's periodic table. If you ever run out of conversations at the dinner table, please. The universe is made exactly of 3 things: X, Y, and Z. Hydrogen is X, helium is Y, and then all the other elements are combined, and they're called Z, about 2%, as I said today. Because, the universe is a complicated place. Who cares about all these elements? They're much more complicated than hydrogen and helium, so let's break it up accordingly, right? X, Y, and Z. You're going to win the trivia with that every single time. But don't we like the details and the little problems? Oh. Just for jargon, I have to educate you also on this. So these stars with the least amounts of heavy elements, these older stars, we term them metal poor stars because, actually, I forgot to say, all these other elements are also called metals for simplification purposes. Any chemists in the room? Sorry, dude. Nothing I can do. Neon is totally a metal. Otto Hahn would not have approved either, but again, I didn't come up with this. So metals, this is all metals, and we call these old stars metal poor because they have a low abundance of these heavy elements, okay? So we just got to live with it. But really, we want the details, right? So here, this one looks better, at least for some of us astronomers. In chemistry, of course, you know that the rows, the columns are important, right? Because they have the same chemical properties, give or take. But for astronomers and nuclear physicists, the rows are important. And so, you see in color-coded here the different processes that get you elements. Some jump. These are the alpha elements. Then these iron peak elements, transition elements. And then in blue here, these are the neutron capture elements. And I want to talk a little bit more about that because that's where the fun begins. And so, I should say everything that's not blue is fusion, and then the other stuff is neutron capture. So let's talk a little bit about that. So I already said where fusion, it goes up to iron. How does this work? This is what happens through sequences of burning stages in the inner parts of massive stars. Eventually, they have an iron core at the very center, but if you try to put 2 iron atoms together, you can't get any energy out of it anymore. It's the end, right? We sit here in the bottom, and so this is when the star goes supernova because it can no longer produce energy, right? But then we do have all these blue elements, so where do they come from? They are not directly made in stars, so we need to work our way there to understand that a little bit better. So let's say you do have a situation where there's lots of iron nuclei. Let's bombard that one with neutrons, just like what they did back then. Here we just use iron as a seed nucleus. And so there are 2 ways you can bombard nuclei with neutrons: in a slow fashion and in a rapid fashion. I'm not going to talk much about the slow fashion. This is illustrated here, but you have neutrons. So this is a piece of the charts of the nuclei. Number of neutrons, number of protons. You add a neutron, it converts it then into a proton. You add that. Sorry, long day. You add your neutrons, blop, 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 one after another, but you always wait until the radioactive isotope that occurs after the bombardment has decayed back into a stable configuration. And then you add another one, and so it zigzags up there. That's good, I like it, but the rapid neutron capture site is much more fun because it kind of goes more like this. You bombard whatever you can onto the seed nucleus, and within 2 seconds, you have all the elements made. This is a timeline of 10,000 years. Who has time for that? Okay. So this is my cartoon version. Let me now show you in a moment an actual simulation of this R process that creates these heavy elements. But before I do so, I wanted to just come back to the play. This is what the Berlin folks discovered. So they had, here is the uranium nucleus. They're bombarded with one neutron. It fissions, but they didn't know what it was. And they observed the barium. And then Lisa Meitner added this piece here to it, right? That you do need to get a second nucleus out and energy. And so that's exactly the same what we're going to look at now. So again, this is the charts of the nuclei. The squared little boxes that you can see here is the valley of beta stability. So these are all the stable isotopes that we know of. I'm going to run this now. It's going to start here with protons as seed nuclei, but same difference as iron. You just have a seed and you bombard it with neutrons and you see what happens. And you will see that it shoots up here all the way into the transuranium region and then decays. And I want you to look at here at this, one of these two is barium, let's say 56. Yeah, so here you will see a pileup. So it shoots, and look at the time here, within a millisecond regime. And so with not even a second, we have all these crazy neutron-rich isotopes made. Then the neutron flux stops and everything decays, diagonally back up. The neutrons get converted to protons. And then it takes some time, but we're still, at a minute or something now, and then it will become stable, right? This is how you create heavy elements within literally a couple seconds. And yeah, there are big pileups here around barium, actually. So if you take these isotopes and per element, sum them all up and look at the abundance distributed, produced in this process, you will get to see this pattern here. So this is abundance as a function of atomic number. And here, this is the barium peak. So elements around barium pile up because of fission cycling processes going on in this thing, right? Uranium nuclei or precursor nuclei, of course, created. They keep being bombarded with neutrons within the R process, and then they fission. And so you have this pileup here at these characteristic peaks, first peak, second peak, third peak, that are a direct signature of that. Now, why am I showing you this plot here? Well, first, I should say, we see the signature in some of the old stars. What does this mean? It means they must have formed from a birth gas cloud where one of these R processes occurred. It occurred, it dumped all the elements into the gas, then our little star formed. 13 billion years later, we observe it, right? I think she would have liked that. I think she would have liked to see that. So here's a spectrum of one of those stars, those R process stars. It's the red spectrum. The black one is like a normal old star for comparison. Here's europium, very heavy element, bombastic line. Here's iron, black and red overlap. And no europium in this normal star, but a bombastic line here. Various other elements, lanthanum, samarium, cerium, dysprosium, yttrium, erbium, cerium, samarium. I'll ask you the elements later. We take data like this with the Magellan telescope that I'm showing you there, beautiful site in Chile, where we take high-resolution optical spectra, such as these here, to explore the elemental abundance signatures of stars, and some of them, small amount, 5% of them do show this R process signature. And here now is a similar plot. Here's the pattern again in blue, and the red dots are not a connection or match to the pattern there, but it's actual abundance measurements in a star that show we do see that abundance pattern in some of these stars. It's pretty amazing. And they all look identical. So between barium and technically uranium, this is a universal pattern that we see in many, many stars by now. So this process just knows what to do. There's not much wiggle room. And Lisa, that one is for you because she liked uranium. This is a uranium measurement If uranium hadn't decayed, the spectrum would like the blue line, but because it has decayed from here to there, if there was no uranium present, it would be the blue line, but there is a little bit here. If it had not decayed, it would look like this, but it had decayed up to there. Sorry about the mix-up. Here is a blow-up. So we can measure pretty much all of the neutron capture elements in these stars, including thorium and uranium, and some even lead. And of course, lead is the product, the decay product of thorium and uranium. They have very long half-lives, so they are long-lived elements. Uranium has 4.7 billion years for half-life, and thorium has 14. So for us, it's basically stable, but technically they're radioactive. All right, so where does the R process occur? That's an age-old question by now. But there has been some progress. But of course, as you probably know, with every door that you open, well, one closes, but there will be more doors right after. So we still have many doors to open. But I'd like to very briefly talk about neutron star mergers. Already before the LIGO confirmation of that this is a thing that is observable from a gravitational wave perspective, we actually saw pretty strong evidence in a small dwarf galaxy for the occurrence of a neutron star merger. But what are neutron stars? For those of you who are new to this in the room, neutron stars are extremely dense, compact, leftover bits and pieces from supernova explosions. Remember, you have an iron core at the end of a massive star's life. During the supernova explosion, that iron core is converted and pressed into a neutron star. So you squeeze all the electrons out and the protons convert to neutrons. You just have a giant atomic nucleus made from neutrons. The diameter is 10 kilometers, but it can have a solar mass. If you happen to have two neutron stars orbiting each other, so you have two massive stars orbit each other, one goes pop, the other one goes pop, you have two neutron stars that still magically orbit each other, which is actually pretty fantastic in its own right. You can end up in a situation like this. Eventually they will lose energy, so they will in-spiral and merge, send out gravitational waves that we can now detect. And then during the merger, you have this explosive event, and guess what? There'll be neutrons galore in this process, and that's exactly what we need for a hefty R process, right? So they had been hypothesized to be R process sites for a long time, but there wasn't any observational evidence. So LIGO has certainly helped to cement that. And so I wanted to just show this to you again with one addition, because I hope you're all familiar with the associated kilonova event that was observed by the astronomers following the merger of the two neutron stars in 2017. So an afterglow in the visible and other wavelength ranges. And I want to show this to you again because that afterglow, that kilonova, is nucleosynthesis in action. You could almost literally see it with your eyes. Because the kilonova is nothing else but the radioactive decay once that cloud moves diagonally, right? The neutron flux stops, and now it decays. It sends out photons. So I'm going to show this again. And now you can witness that kilonova that occurred in that neutron star merger. So this is still during the bombardment, and now, and this runs now on the time scale of several weeks, which was the time scale observed for that thing to fade, that radioactive decay light is the kilonova. And I think this is really neat, right? Because we can actually never really see the fusion inside of stars. We know that it's there because we calculated it and we compared it with predicted observables for the surface of the stars. But we have never really seen it. Here you can see it. You can almost take a picture of it. I mean, you map it out and you observe a light curve, individual measurements of that brightness, of that decay brightness. All right, so, and as I said, before LIGO, even 1 year beforehand, we had observed stars in this dwarf galaxy that it is here, trust me. If you don't see anything, that's fine. There's much to see. This is the smallest, faintest, wimpiest galaxy that we know. It only has a few thousand stars. we do know that it's a galaxy, so you got to trust me on that too. And it's one of the satellite galaxies of the Milky Way. So it's just a tiny thing that's orbiting the Milky Way, waiting to be eaten, because that's what big galaxies do. They eat little ones. We observed 9 stars, and 7 had that R process pattern. Here it's purple now. You see, we made a bunch of measurements. They follow that pattern. The gold one is the S process. You can clearly see it's not an S process thing. The pattern of the R process matches, even in the case of here, where we only have 2 elements. Definitely R process. So now you have a small galaxy, really tiny. You have a massive R process event. It has the same energy as a supernova explosion, 10 to the 52 ergs. That's quite a thing. And you need like enrichment that kind of works and explains what we have observed there. So to cut a long story short, this is the punchline here. These abundances in the reticulum are the big fat red dots here. They're really high. That's all you need to take away. Much higher than these ones. And these are upper limits, not even measurements, of barium and here europium of stars in other little dwarf galaxies that are also orbiting the Milky Way. So just, from a comparative perspective, most, N-1 dwarf galaxies show very, very low levels of heavy neutron capture elements, except for the stars in reticulum 2, 3 orders of magnitude higher, right? So you need a really prolific R process source, and as we've calculated, and of course others before us, neutron star mergers give you a very prolific result, whereas supernovae are not really having enough oomph to get through all the heavy elements. Now you could say if you're clever, saying like, Anna, supernova everywhere, lots of them. Why don't we just take 1,000 supernovae to bump up the yield, right? But here's the cool thing. What would have happened to that little dwarf galaxy if you dump 1,000 supernovae into the system? It would have blown apart, but this thing is around. It's going around the Milky Way. So that constrained us to say, okay, there were a few supernovae. A little bit of that stuff needs to be produced. That's fine. We want that, actually, a little, because it explains normal birth environments. But once in a while, you're lucky, and there's a neutron star merger. They are rare. And when it happens, you go all the way, and that's when you get that. So good evidence that neutron star mergers are a major source and site of the R process. There's additional data that I can't show you today, but they suggest that definitely there is room for another site, perhaps some magneto-rotationally driven supernovae or jet supernovae or some other quirky things where you have more knobs to turn as a theorist to kind of give it enough energy and juice to really go all the way to uranium and not peter out around the first peak, which has been shown to be the case for normal core collapse supernovae. So there's room there. That's why I said we have more doors to open, but at least we have 2 pieces of evidence now. Reticulum 2, this dwarf galaxy, as well as the LIGO event, that neutron star mergers do play a very important role in the production of heavy elements in the cosmos. And so with that, I want to say heavy elements are produced all across the universe ever since the earliest times. And by studying the oldest stars, we keep finding evidence of it. Until we know the exact astrophysical site, how cosmic environment shapes element production, and what all the nuclear physics details are. So we can all thank Lisa Meitner that we know today that our jewelry has been made billions of years ago throughout cosmic history, and that we are wearing the products of neutron star mergers and supernovae and other fun things going on there. So remember that, if nothing else. And again, thank you to STEM on Stage for the collaboration to come to bring this play to life, Living History Theater. It was inspired by this film that exists about Marie Curie with this actress here, Susan Marie Franchek. And yeah, we hope to push that a little bit further and eventually also turn it into a digital theater presentation. So you have seen a work in progress, and hopefully it will get better with time. And if you are in general curious about elements now and the origins of the elements in the cosmos, a long time ago I had apparently too much time on my hands, so I wrote a book aptly called Searching for the Oldest Stars, because that's what I do. If reading isn't for you, and I totally get it, you can watch my YouTube series. That's the short version of the book. I'm happy to take your questions as well. Thank you.
Let's take just a few questions if we have time for.
How often does a neutron star merger occur in a galaxy like the size of the Milky Way?
I don't know the exact number, but it's not a lot, because it takes quite a while for these things to in-spiral. The shortest times that the theorists can sort of cook up is something like 30 million years. It's much more likely that it takes 1 billion years or something, or longer. So given that, and then again, you need to have a situation where you have two massive stars orbiting each other. So first you need to form those in the right kind of way. You get two massive stars, and then they need to turn into neutron stars and not fling one out of the system. So there's a lot of chance encounters kind of that need to happen. So I don't know the exact rate, but it's not a lot.
And is the neutron capture just a local event then around the collapse of the neutron stars, or does it affect a wider area?
It's reasonably local. Yeah. It depends a little bit. So, for example, if you take a small dwarf galaxy in the early universe, you have an process event there. That means a huge energy injection into this local region, right? And if that is mostly what the galaxy is all about, then it would actually puff up, and then it needs to cool down. So that would have an effect on the entire dwarf galaxy, because it gets mixed and kneaded like dough, essentially. Whereas in the Milky Way, if you have a larger region, there would be less of this sort of energetic dynamics occurring. Well, yes. Do I know anything about the creation of dark matter and what it consists of? Unfortunately, I don't. I don't think anyone knows. If I had the answer, I would probably win the Nobel Prize. So thank you for bestowing that on me. We know quite well that it exists, because it can be mapped. The stars feel it. The stars are basically blind, but they feel matter around them, and they can't distinguish between luminous matter and dark matter. So they only feel matter. And so they're swimming in this matter sea, and we see how they move. And so from that we can deduce, because we can see the luminous matter, we can measure, okay, how are they moving, and then what is this leftover bit that then we attribute to dark matter. So we'll have to wait and see. Maybe in your lifetime we have an answer, but maybe also not. It's a really difficult problem.
Question up in the back.
What's your favorite kind of star or structure within the universe?
What is my favorite star or structure in the universe? Well, I really like the tiny dwarf galaxy. They're cute. And there's only so much you can do to them, right? So they really constrain our interpretation, because you can't destroy them. And of course, I have several of my old stars that I really like. AT 3027 minus 2326, or AT 1523 minus 0901. So I've grown to like a whole bunch of
Are
them.
those pet names?
No. They're their actual names. I didn't give it to them. They're based a short version of an old coordinate system used for them.
There's a question up here.
talk about like Louise Meitner and Marie Curie. Maria Goeppert-Meyer, she's the atomic nucleus scientist, the shell model, Maria Goeppert-Meyer. Since heavy element, probably you can consider a future play about her.
Yes, I'm happily willing to take names. If you can also fund this, that would be great. Because I do this in my non-existing spare time, you must know.
Any other questions for Dr. Friedel? We've got one up here.
I just had a question about, we talked about the fact that supernovae don't have our processes happen as much. Do you point to what's the biggest factor that prevents those processes from happening in supernovae that something like a neutron star merger has? What are some specific factors?
So I think to some degree it's a little bit unclear because the devil's in the detail, and supernovae on their own are actually hardly understood. There's a lot of things that we think we know about it, but nobody can simulate a 3D explosion, for example. And it gets even more complicated with neutron star mergers because you actually have different components of it that spew out, ultimately heavy elements. It gets quite complicated. But I think just common sense tells you that obviously, energy plays a role in the sense of that you need to have a strong enough you need to have enough neutrons so you can have a strong enough neutron flux that lasts in that strength for long enough. It may only be 2 seconds, but if you run out of neutrons, you are not going to make it all the way to the transuranian elements that then decay. So maybe the proton-neutron stars that are developing in the supernova just cannot provide that because, again, if you contrast with the neutron star merger, they're shearing the neutrons out of each other when they kind of inspiral and deform and scrape, at each other. You're ripping out neutrons more and more and more. That sort of violent process doesn't occur in the making of a proton-neutron star, right? So you have lots of neutrons around, but so that's sort of the best guess. But the details of how to get there is TBD.
So I think Dr. Friedel's going to be available for a little bit in the atrium, especially if any of you future scientists want a chance to meet and talk with her. But in the meantime, let's thank her again for an excellent